Okay, so a quick summary of what we had seen in this lecture, because we saw in quite a bit. So we saw DAGs, directed acyclic graph. Directed graph that don't have cycles. Those graphs are very nice, and in some cases they're easier to handle than undirected graphs. In particular, they induce topological orderings. You can number the vertices of the DAG in such a way that edges always goes from a small numbered vertex to a large numbered vertex. Then we saw DFS on directed graph, how it provides us with pre and post numbering on vertices. And then we went down the rabbit hole of strong connected components. We showed, so first when we have a directed graph, the equivalent of connected component in undirected graph in the directed graph is strong connected components. Strong connected component, if you collapse them into vertices, the resulting graph is this metagraph that is a DAG of strong connected components. And amazingly enough, there was a DFS-based algorithm that ran in linear time and could compute both the strong connected components and the metagraph. And this algorithm really relies on some very simple properties of DFS, but as I said earlier, this algorithm is really a clever algorithm. And the algorithm we see today are used all over the place because dependency graphs are very important. So it's really important to be able to detect cyclical dependencies. Graphs like that are used for preferences handling. You have rankings and you want to figure out the information ranking you have, what is clearly the best, what is the worst, what are in the same strong connected component are more or less equivalent, etc. So those both DAGs and strong connected components are being used widely, and it's really useful to be able to think about them and be able to, of course, design algorithm for them. And that's it.